Good morning, and once again welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamopa. And I've just introduced pure mathematics for topic number 6, integration. The main topic is integration, and I've said this is a main one, and you have to pay very close attention to each and every example explained here. And we have said that in case we have a curve that is defined parametrically, the area is going to be given by t is equals to a, t is equals to the limit of t of the function gt f prime t dt, and this one is already explained in video 1, so I will not go back to explain this, but I'll use it to explain example 1. And example 1 is saying that a curve is represented by the parametric equation x is equals to t, y is equals to 3t squared, and then the question is find the area under the curve from t is equals to 1 to t is equals to 2. Those are the limits. And of course, as understood in video 1, we start with the general formula. A is equals to the integral of y dx. And at this particular point, we know x is equals to t, and therefore dx dt is going to be equals to 1. So at that level, we can already make dx the subject of the formula here and say, after cross multiplying, dx is equals to dt. So this one will help us a great deal in substituting for dx. And therefore, because we wanted now to substitute or to get the area within this region, then we have a is equals to the integral of y, which is already in terms of t, 3t squared, dx, and dx is dt. And because all the details are about t, then we can bring in the limit of t, which is 1 and 2. And it goes without saying, now the only thing we need to do is to simply integrate generally, and it's going to give us 3t cubed over 3, and then we can bring in the limits 1, 2, which is easily, these 3 cancels with that, t cubed 1, 2, and this goes without saying. When t is 2, we have 8 because of 2 cubed 8 minus 1 cubed 1, and the final answer is simply 7. And that is simply like the end of the story. We have understood it that way. And I think in the same video we can explain example 2, which says that a curve is represented by the parametric equations x is equals to the cosine of t and y is equals to minus the cosine of t. The question is find the area under the curve from t is equals to pi over 6 to t is equals to pi over 4. That is it. And of course, we start with a general approach. The very general formula learned in pure mathematics 2, we say, let a be equals to the integral of y with respect to x. And at this point, we say, we know x is equals to the cosine of t. And this means that dx dt is equals to what we know minus the sine of t. Minus the sine of t. And from this, then we can make, because our biggest desire is to replace dx with something that talks about t. And from here, dx is minus sine t dt. And therefore, the area becomes, hence, area becomes the integral from pi is equals to 6 to pi is equals, pi over 6 to pi over 4 of the y, which is minus the cosine of t. Now the dx comes in handy as minus sine t dt minus sine t dt. Fine. At that particular point, we know that this one is going to be positive, and it's going to be positive, so the area is going to be the integral of all the way from pi over 6 to pi over 4 of cos t sine t dt. Why? Because the negative times negative gives us positive. But we do not have a direct integral of cos t sine t. So we will have to rewrite this one in a specific trigonometric identity that will give us a direct integral, or that can be integrated directly, and we have something like this. So we have no direct integral of this, but we can have a trigonometric identity. We know use sine 2a is equals to 2 sine a cos a, because our format is in this case it's in sine t cos t, which must be equals to a half sine 2t. If this is true, use sine 2a is equals to sine a cos a, and because we do not have 2 here, we have just 1. That means we divide by 2 to get this, and meaning that we must divide by 2 this one to get this. So we are now already having our area to be equals to the integral from all the way pi over 6 to pi over 4 of a half sine 2t dt. Sine 2t dt. Fine. If that is true, then what is the integral of sine 2t? Is obviously the integral of this becomes 1 over 2 times 1 over 2, because we have 2 here. A half times half is a quarter, is going to be, and in fact minus a quarter, because the integral of sine is negative cos, minus a quarter cosine 2t, and then we apply the limits pi over 6, pi over 4. And it goes without saying, then the area is going to be minus a quarter, and the cosine of 2t when t is pi over 4, which is now going to be cosine pi over 2 minus minus a quarter cosine pi over 3 when we substitute it with the lower limits. And this one gives us, you can already see there is a negative 4 which is common. Is going to give us minus 1 over 4 rather, and inside the bracket we have the cosine of pi over 2, of course, plus, because no, it's going to be minus, such that when you open this bracket you're going to have plus as a device there, the cosine of pi over 3, and that is it. So it goes without saying that the cosine of pi over 2 has to be understood. The cosine of pi over 2 is, of course, 0. The cosine of pi over 2 is 0. So we have minus a quarter, open the bracket, we have 0, minus, then the cosine of pi over 3, the cosine of pi, the cosine of pi over 3, which is going to be equals to a half. So minus a half. Close the bracket. Minus a quarter multiplied by minus a half is obviously going to be positive an eighth. And that is the final submission. And as far as that integral is concerned, then we have been able to get the area under that curve between the limits expressed in the question. Of most important is how we moved from this, how we move from this to this. It's how we move from this, because we could not get the direct integral of that, how we identified trigonometric identity that can explain this, and we got half sine 2t, which we eventually integrated. Yes, go to my YouTube channel, subscribe, and of course share widely, and let us see what we can do to move forward. All right.